Thank you very much for the warm welcome. I'm David. This is my collaborator, Ali, over here. I'm going to be handing over to him about halfway through the talk. And yeah, today we're presenting to you RADSan. We're quite excited about it. Yeah, I hope that at the end of the talk, you folks will be as excited to try it as we were to develop it. So if there's one slide that we'd like you to take home in your minds when you're leaving this talk today, it's this one. And this is just an executive summary of what RADSan is. So it's an automatable, real-time safety testing tool. What it is, it's a customized fork of Clang, and it's got an extra sanitizer baked into it. That real-time sanitizer's job is to detect what we call real-time safety violations at runtime when they happen. And what does that look like? Well, as a developer, you're able to, at the granularity of your choosing, add this attribute, this real-time attribute, to functions that you need to be real-time safe. And then if at any time you or any of your colleagues introduce a real-time safety violation, like this memory allocation right here, in your real-time context, and if you've compiled with this simple compiler flag, just like the other sanitizers you might be familiar with already, then at runtime, RADSan detects this violation, tells you exactly what went wrong, in this case, malloc. And it gives you a nice little stack trace as well, so you can locate the problematic line of code straight away without having to do any sort of analysis. So this is what we're going to be talking a little bit about today. I'm going to lay the scene a little bit, talk a little bit about the problem space and what strategies we've got already to answer the question, is our code real-time safe? I'm going to do an introduction to sanitizers, for those of you who aren't already regular users of them. At that point, I'm going to hand over to Ali, who's going to talk through the design and implementation and how we built RADSan. We're going to show you how to use it, talk a little bit about where its boundaries are, what it's limited by. And then, yeah, it's open source, so we're going to show you at the end how to get it. So even if you're a really experienced real-time software engineer, chances are you've probably, within the last few months, asked yourself a question like, does this allocate? Like, I'm pretty sure it doesn't, but are we sure? I don't know. And maybe you're looking at some code a little bit like this. Maybe you've got two invocations of a stood function. You're constructing that with lambdas that are effectively the same, but they've just got different capture lists. And, you know, how many of these allocate? 0, 1, 2, both of them? The point of this slide is not to tell you what the answer is. We may not know. But the point of this slide is to just make the point that it's not immediately obvious. And changes, like adding this extra element into your capture list, are easy to miss in something like a code review. So it's that question of whether this allocates is a specific one in a broader category of questions that are kind of like, could this block? Is this an operation that could block? You might be staring at the API of some third-party network API. You know, you might be looking at like a very big library dependencies entry point and thinking to yourself, can I do this on the audio thread? Is this something I can do in a real-time context? And really, you're asking yourself, can I do it in a real-time thread? So answering that question is not easy. And thanks to amazing conferences like this one, and thanks to the generosity of the folks listed on this slide and others who I didn't have space to list on this slide, there's a wealth of learning resources out there that you can go and read, you can watch talks and find out what is and isn't okay to do in a real-time context. But we're concerned here with a slightly different question, a very slightly different question. And that question is, how can we be confident that our code is real-time safe? Keyword being our code. And that our could mean, you know, like a team's code. You know, you might have a team working on disparate parts of a code base. How can you be confident that the code as a whole is real-time safe? Or maybe it's just one person. How can you be sure that your specific code is real-time safe? And so what strategies have we got to address this already? Well, this isn't a normal kind of like product talk. I'm not going to say the situation's bad, because it's not. The situation's great. We have a load of amazing tooling at our hands to answer this question. And, you know, we have shared experience. People who have spent lots of years doing this stuff can educate those who haven't. That's great. We have code review, profilers and debuggers and other instrumentation like strace or dtrace. They can tell us a huge amount. We can break in system calls. We can trace system calls. That's brilliant. Plugin val. Who uses plugin val? Show of hands? Yeah, what a fantastic tool that is. Right? That's brilliant. That can catch whether we've allocated like in a function that's meant to be used on a real-time thread. What else have we got? We've got static assertions. That can tell us whether atomics are lock-free. We've got documentation for our big APIs. Hopefully, if the library maintainers are diligent, they will tell you. And we thought it was worth mentioning. We think using your ears is woefully inadequate, but you know, sometimes it's the first indication that something's wrong, and you know that's we thought it was worth mentioning. But you know, there's like, it's not without, each one of these isn't without its downsides. You know, like getting experience takes a long time, and accessing people with that experience is a privilege. And code review is prone to human error. Profiling and debugging is great, gives you the information you need, but it's a manual process and it can be slow. Plugin val is really focused on plugin APIs. Static assertions are limited, documentation goes out of date, clicks and pops are very unlikely. And what about pre-built binary dependencies? What about those? And you know, these are fantastic tools, and they can give us together, when used well, great confidence that our code is real-time safe. But you know, what if we can maybe contribute a little bit of an improvement to this situation? What if we had a tool that could tell us? So we thought about it a while ago, and we thought that, you know, a nice tool would assess real-time safety, yes. It would have runtime awareness. So, you know, sometimes pushing back into a vector isn't such a big deal if you've reserved a load of memory. It would detect a wide range of violations, even from third-party dependencies. Ideally, it would point you directly to the problematic code. It'd be nice if it was fully automatable and be able to fail a CI pipeline. Wouldn't that be cool? Like, somebody's made some seemingly innocuous change in one part of the code base, causes a real-time safety violation elsewhere, and we fail the CI pipeline. That's what we're looking for. That would be great. And you know, similar tools like this do exist, and you can probably see the next slide come in, and that's, we think sanitizers fill some of that gap. So if you haven't used sanitizers before, they are tools provided with your compiler that can detect a bunch of problematic situations. So a just sanitizer can pick up all sorts of memory errors at runtime, things like trying to use memory after you've freed it, trying to read outside the bounds of a vector. Thread sanitizer will detect data races for you, and UBSAN, or undefined behavior sanitizer, can pick up these things. And using sanitizers is really simple. It's literally just a case you compile with this compiler flag, fsanitize equals address, and at runtime you get an error message telling you what went wrong and pointing you to the problem. So how do sanitizers actually work? This is where it gets interesting. In order to understand how sanitizers actually work, we need to kind of take a couple of steps back. And this first step back, we're going to think about compiling and running a C++ executable with LLVM tooling at a high level. So I'm sure everybody's familiar with the concept of having some C++ code. You know what it looks like. We feed it into a compiler, and on the other side, we get our binary executable, something like ELF format. And you're probably also aware that, you know, in the middle there is some sort of intermediate representation where optimizations happen, and this is really nice because you can compile any language and down to any target architecture binary, and use the same optimizers. That's great. It's really powerful. But in order to understand how sanitizers work, we need to dive a little bit deeper than that. And so let's take a look at a more detailed tool chain. Our developer, a process there is a white box, and a physical thing is a black box. Our developer provides some C++ to the tool chain, and the first thing that gets given the C++ in the tool chain is the preprocessor. That expands your includes and other macros until you get your translation units. This might be familiar to many of you, but translation unit gets fed through the parser, and out the other end you get your abstract syntax tree. That syntax tree goes through a process in LLVM at least called code gen, and the code that's generating is this LLVM intermediate representation, or IR. This IR gets optimized through an optimizer, and out the other end comes more IR. Our compiler backend translates that IR down to some target-specific assembly code. That assembly gets fed into an assembler. Out the other end comes our binary object code. And finally, final stage, our linker pulls together some libraries that are on the system, namely the system library, C++ runtime, and some other third-party dependencies that you might be linking in, until finally we get our executable. And so you'll probably recognize that the stuff on the right-hand side, anybody want to tell me what the stuff on the right-hand side is? Anyone? Any thoughts? That's Clang. And this is where sanitizers fit in. So there's three main areas where sanitizer implementation lives. First is in the code gen. When a sanitizer wants to, inject logic, it gets injected into the IR. Secondly, in the optimization, if the sanitizer wants to, change the way some logic works, it will do it there in what's called a sanitizer pass. And finally, most sanitizers will also have some sort of runtime component for anything that needs to be detected at runtime or changed then. All right, so we think the easiest one to understand is address sanitizer, so we're going to use that as an example. Now, address sanitizer doesn't use all three aspects of this diagram. It's actually kind of only got two parts of it. There's a sanitizer pass and a runtime. And this is what they do. It's actually fairly straightforward to understand. The runtime library does what we call intercepts, malloc, and free. I'm going to come back to what interception actually means in a moment, but just think about it as, it picks up malloc and then replaces it with its own implementation. And what that implementation does is it allocates a bit more memory and poisons memory either side of what the user asked for. What poisons means is too detailed for this talk, but you can think of it as something that is detectably bad. So if the user is asking for a memory allocation of this size, what the interceptor actually does is it allocates this much and then poisons that. And the implementation is clever enough to make sure that we don't have kind of like chunks of poisoned memory in spaces which are meant to be contiguous, like in a vector. Now the pass that happens at compile time, operating on the intermediate representation, just all it does is it transforms every single memory access into a checked one. And that check saying, is the memory poisoned? If yes, report an error. If no, carry on as normal. So if it were written in C++, it would transform some code that looks like this, trying to access some memory, into one that takes an address, checks if it's poisoned, reports an error if it is, otherwise carries on. And that's it. That's it. Okay. I think I've got another few minutes. So let's have a look at how interception works. So what is it? It's the process of replacing system calls, usually in libc, with customized implementations. And what that allows us to do is any and all of the following. At runtime, we can detect those system calls, we can change the behavior of those system calls, and we can actually call the real system call as well. And with those three together, that's a really powerful situation to be in. We can do a huge amount. And the really smart people who work on LLVM have written tooling, have written some macro magic that allows people who don't know what they're doing, like Ali and I, to write platform-independent interception code that's really quite straightforward to understand, no matter how complicated it is out the back. So here's an example interceptor for malloc. This might be something that just logs the fact that malloc happened. If some condition holds, do something else, otherwise call the real malloc. And how that works on macOS is a little bit different to how it works on Linux. So I'm going to talk through that fairly quickly. Interception is actually directly supported on macOS using a dynamic loader feature called interposing. And how that works is like this. So when the dynamic loader loads a macro binary, and if it finds a pair of function pointers in this special data interpose section of the binary, it treats that as an instruction to reroute all calls from one function to the other. So that's really, really very powerful. And it's even smart enough to know that if you try to call the real one from within the one that you're replacing it with, it will just call the real one. So it's really very clever. And so what that looks like is simply just a struct of function pointers. And this macro magic expands out to a couple of declarations. One is declaring the real function, one's declaring one to wrap it. Inserting one of these pairs of function pointers into the data interpose section. And then here we go. Here's our first red brace from our own implementation. And this is just expanded as follows. So that's how it works on macOS. On Linux, it's a little bit different. It's more straightforward to replace a function on Linux. So if the symbol is defined in your executable, that's going to get found first in the search order. Calling the original function is a little bit trickier, and how they've set up the interceptors in LLVM is they use the symbol lookup with DLSim to actually just find the next symbol in the search order. So that expands out to something like this. And I think it's about time that I summarized. So yeah, as a summary, to instrument your compiled code, sanitizers exploit three things: intermediate representation code generation, intermediate representation optimization passes, and runtime interception. But how are these ideas useful for testing real-time safety? And this is where I'm going to hand over to Ali, who's going to talk you through how we did that.
Cool. Thanks, David. So now that David's explained how interceptors can be useful and sanitizers in general can be useful, let's talk about how we designed and implemented RADSan. So let's just recap on some of the requirements. We want to be able to detect things at runtime rather than kind of analyzing the code before it gets compiled in some kind of static way. We want to be able to detect a wide range of violations, allocations, locking threads, or things like that. We want to be able to detect violations that occur inside closed source precompiled binaries. So if you've been given a library developed by a third party, you still want to have confidence that you can use this on your audio code. We also want to be able to define the real-timeness of any code so that you can have control over the kind of granularity of what you're defining as audio code. We also want violations in automated tests to cause CI pipelines to fail so that we don't end up merging bad code into master and release it. It should be easy and quick to use for obvious reasons. And errors should point to, well, you should be able to use the output from the sanitizer to tell us exactly which line of code caused the problem. So I'm just going to go back to this diagram that David introduced earlier of the sanitizers, and the RADSan runtime that we've introduced adds two areas to LLVM and Clang. There is the codegen section here on the right, and then there's also a runtime library that gets linked to at runtime. So what do these two parts do? Well, firstly, the codegen is quite simple. It basically looks for all functions that are marked with the Clang real-time attribute, and then adds in a call to RADSan real-time enter at the beginning of this function, and adds in a call to exit at all the function exit points. This then works with the context that we've added to the runtime, which implements these functions and basically just keeps track of whether the current thread is inside a real-time context or not. It also handles any errors when it detects violations. We have a few different modes for handling errors. There's exit, which will, as soon as you hit its runtime violation, it will exit the application with a non-zero return code. Very useful if you're using this as part of your CI pipelines. Then we have continue and interactive modes, which continue will just continually run and checking violations and then printing in any output to the terminal so you can inspect. You can leave it running for a while and inspect afterwards to see what happened. And then there's also interactive mode, so you can kind of step through, similar to like you would running a debugger. The other part of the runtime are the interceptors they've talked about. Our interceptors that we use, they're pretty simple. They only do a couple of things. They firstly check whether we're inside the real-time context. If it is, then we will report the error. And then afterwards, it just returns the actual system call. If you're in the exit error handling mode, then that real system call won't happen because the program has just exited at that point. But if you're in continue interactive modes, then it will just return the real system call. So that's what they look like. We just have the first line, which checks whether we're in real time and handles the error, if so, and then just returns the real system call. So how do we decide what functions to intercept? If we look at a C++ application in terms of kind of layers of interaction with the underlying operating system kernel, then we have, at the top here, we'll have our C++ application that we've written. We'll have written lines of code along the lines of these. We've got scope using scope blocks, or maybe call make unique. This at runtime, this will then link to the C++ runtime library, where we'll have implementations of things like std lock and the implementation of new, which these other functions would have called. That then will link to the libc library, calling things such as pthread mutex lock and malloc and free and the various cousins. So yeah, if we look at these layers as a kind of funnel with everything kind of going through the C standard library, then this is the best place for us to intercept. And also, if we use a third-party library, we can see that this third-party library, even if we can't see the actual source code, we'll still be using the same C standard library to go through in order to call into the kernel. So yeah, what do we intercept? Here is a mostly complete list of things we intercept. The main areas are the memory allocation with malloc and free and various other functions, and then the pthread interface, where we intercept not everything on the pthread interface, because things like pthread mutex trilock should be safe. If you saw Fabian's talk this morning, he talks a bit about that. But we intercept all these other functions so we can detect when potentially blocking calls to the thread, to the pthread system happens. But we've also added interception for things like file systems, streams, and sockets. I suspect things have gone very wrong if you've ended up trying to talk to a network on your audio thread, but we've added it anyway, just because it's easy to do. So how do we actually use it? I'm now going to attempt to do a live demo. Mouse down there, okay, yeah. Okay, so here we have, hopefully, such a simple example, it can't go wrong. So here we have a very simple application. It just has one function, this process call, which is our real-time, this is our audio callback. We've mucked it here with this Clang real-time attribute. And then we could just call it on in main. So in order to compile it, it's quite simple. We just call Clang++. We then pass in fsanitize equals realtime. Oh no! Sanitize equals realtime. And then we just add our file, and we're going to call and run it. And hopefully, excellent, we now have this stack trace printed out. Real-time violation, intercept a call to real-time unsafe function malloc inside real-time context. If we look at the stack trace, we've got the interceptor is on, here, in this line here. Line 4, we've intercepted this is a call in malloc inside our interceptors. And if we scroll down, sure enough, we can see this vector constructor here is allocating. So let's go back to the slides. There we go. Oh, live demo, just done that. So I'm going to do a little bit of audience participation here. I have, again, a very simple example. We have an atomic with a struct of 2 doubles. And inside our real-time function, we are storing and loading this atomic. Now, does this cause an error? The answer is very much dependent on the platform you're running on. I'm running on this. This was run on my M2 Mac. You're running some version of macOS. I can't remember. So I'm going to do a bit of audience participation here. Who thinks this will allocate in any way? Is that? Who thinks it definitely won't allocate? Lock, sorry. Sorry, let me do that. Who thinks it will allocate? Who thinks it will lock? Who thinks it won't lock? Okay, well the answer is, we're all good. This didn't lock in this situation. So our 2-dimensional audio application was such a success. Someone wanted it in 3D. Someone came along and added the third dimension, the Z dimension. The rest of the code is exactly the same. Who thinks this will lock? Okay, and who thinks this won't lock? One person. And it does lock. So here we can see on line 2, we've intercepted a call to OS spin lock lock. And if you look down at line 4, you can see inside the, it's got the pseudoatomic store, which is causing a lock. So in this example, a pseudoatomic can't always guarantee to be lock-free, and it's kind of dependent on the size of the data you're trying to protect. So yeah, we think this is a good example of as someone's made an innocuous change, and it will now cause our CI pipelines to fail. Here is another example. Here we basically have a lambda that's being invoked via a std function. That lambda is capturing an array of 3 floats. Does this cause an error? Who thinks this will cause an error with the RADSan? Okay. And who thinks this won't cause an error? Slightly more for won't. And yeah, we're all good on this one, in this situation on my machine, just to be specific. Here is another example. It's exactly the same as before, but instead of an array of 3 floats, we've now got an array of 8 floats. So who thinks this won't allocate? A couple of people. Who thinks this will allocate? Slightly more people. And the answer is, yes, it does allocate. You can see on line 2, we've intercepted a call to malloc, and on line 11, inside that horrible-looking templated code, we have a call to inside the std function constructor we've allocated. And for those that aren't too sure what's going on there, a std function needs to store whatever it's capturing somewhere. If that's a very small amount of data, then it will be able to do it without allocating, but above a certain point, that will need to allocate new memory, so it will do that upon construction. I'm going to skip over these next few examples. I think we've seen enough. So yeah, limitations. I've shown you what it can do, but let's perhaps talk about what it can't quite do yet, or what it could do better in the future. So we've been intercepting system calls, which is one kind of set of things you shouldn't do in some real-time code. But there's another set of problems which are kind of more to do with algorithmic complexity, especially kind of amortized algorithms that have amortized complexity, which basically means that every so often you might have it might do a lot more work than every other time. So we can't really use these sorts of functions on an audio thread, and we think that's quite a difficult problem to be able to detect, really, unless you knew exactly which ones you didn't want to intercept. Inlining, the compiler might inline some of these calls, and so they might not get intercepted. We're not quite sure exactly how bad of a problem this is, and whether things will get missed. I'm fairly sure if the system needs to get more memory, it's going to have to call into the kernel by the C library at some point. So I think we might be safe for that one, but some of the others, I'm not too sure. Maybe needs a bit more exploring, I think, to understand that problem. Is the list of intercepted functions complete, or maybe have we got things that it shouldn't be? I mean, yeah, we're still this is a fairly early stage where we're working on this. So yeah, any insight into what we should be intercepting, what we shouldn't be intercepting is very welcome. Yeah, granular deactivation of interception. Yeah, currently we've just, you either have to have all interceptors on and off, but we think it would be very useful to be able to turn some of them on, some of them off, so that you can have greater control over what you want to actually intercept. And also similarly, we've also added the ability to actually turn RADSan on and off inside some code. So you might want to ring fence some blocks of code to say, like, yeah, we're fine with what this is doing inside, please ignore this. There's also, potentially add some parameter-aware interception controls. So some of the system calls, particularly ones with like file reading rights, have flags that you can pass in, which actually mean that these functions will not block. So we can potentially add the ability to check these the arguments that you're passing in and see whether this call is actually real-time safe or not. But yeah, it needs a bit more investigating over what system calls are fine and which aren't. In order to use RADSan, you've got to use this forked version of Clang, which is not ideal in many ways. You might, with the other sanitizers, you can use the specific version of Clang that you are using in production. So having to use this forked version, it makes things a bit harder. You have to get hold of it, and you might get out of date, etc., etc. But yeah, we've been thinking about how to kind of mitigate this problem a little bit. There's no Windows support at the moment. You can use Clang on Windows. I suspect most people use MSVC on Windows though, so it might be of limited use anyway. But if anyone wants to contribute or give us any ideas, then yeah, also very welcome. So getting hold of it. There's a couple of ways of getting hold of it. We've created a Docker image, which you can pull using this address here. Docker pull realtime-sanitizer RADSan Clang. This contains a Ubuntu image, which just contains the precompiled version of the precompiled fork of Clang and the whole LLVM project. So you can just pull that and then you can start compiling straight away. It does mean you have to be compiling inside Linux, but we still think it's very useful even if your main target is Mac. You can also access the whole repo via GitHub. So you can download this and build it locally and run it. This contains a submodule, which is the fork of LLVM project. It's very big. It does take a long time to build, especially on slightly older machines. It's quite painfully slow. Although much faster if you use Ninja rather than Make. That was something we learned the hard way. But yeah, it's available if you want to kind of build it and run it yourself. So yeah, thanks to Matt for doing some testing for us. Where are you? I'll say no. Thanks for Fabian for some insight into glibc and also some useful things in his talk this morning. So yeah, thanks to ADC for having us and you for listening.